So first, I would like to acknowledge my co-authors shown on the slide here. Uh, we'll talk about the interaction of the urban pollution, energy balance, and the boundary layer dynamics in Beijing. So we all know quite well that the boundary layer dynamics is driven by the incoming solar radiation, and similarly also that the aerosols in the air affect the boundary layer height. So when the aerosols attenuate the incoming solar radiation, we have less energy available at the surface, so less vertical mixing, and therefore also lower boundary layer height. Similarly, also in the upper layers of the boundary layer, especially black carbon and other aerosols, absorb heat, which then stabilizes the atmosphere, which also reduces the vertical mixing and therefore also the boundary layer height. Similarly, also the urban heat island effect is reduced because we have less energy at the surface. So the urban heat island intensity is much smaller. Therefore, also then the urban heat island induced circulation brings less than the cool and cleaner air outside of the city into the city. That's why we have then smaller boundary layer height, where the pollutants accumulate in a smaller space, bring the concentrations up, which then further lowers the boundary layer height, and we have a negative feedback loop before because of that. As I said, I will show you results from Beijing. In Beijing, it is quite well researched, this phenomena, especially in the winter months, but also mostly and almost only in winter months. But there is quite strong seasonal variation in this effect, and I will show you the seasonal variation and also very plausible reason for it, how it affects the surface urban energy to this boundary layer dynamics. So this study was made at our Beijing University Chemical Technology BUCT site, northwest of Beijing, here just outside of the Third Ring Road. This is jointly operated by the University of Helsinki and Beijing University of Chemical Technology. This site. It is very typical residential or campus area in Beijing, where we have the observations here at the top of this teaching building in the west campus of the BUCT University. So next, I know, very annoying table. I'm not going through it. I expect you don't go through it either. You probably can't even see it. This is just to show that we have a very comprehensive set of observations in this site on aerosols, trace gases, meteorological observations, and so on and so on. So instead of going through this, you can check the paper. All the information is there if you want to see more details. The meteorological data, the PM2.5 data, boundary layer height, everything is from this site using the observations also described in this paper. But unfortunately, we don't have flux observations there because we weren't able to build the mast, at least yet. It is work in progress. Hopefully, they allow us to build the mast so that we also can get the flux observations there. But instead, the fluxes were simulated using the surface urban energy and water balance scheme called the SUS. It was forced with the meteorological data from this BUCT site. And it has been evaluated in Beijing by these two papers, by Kokkonen et al. And Cheng et al. And it is performing rather well in Beijing. So the fluxes simulated by the model should be quite reliable to use also with the observed meteorological data. And then to the actual result. So if you first look at the right-hand side column here, we have the boundary layer height diurnal cycle in different seasons. So we have the winter, spring, summer, and autumn on clean conditions with the blue and the hazy conditions with the red. So you can see, especially at the daytime, we have a quite significant reduction of the boundary layer height because of the PM2.5 level within the boundary layer. There is quite big variation. You can see that the effect is very strong in spring and autumn months, but in summer months the effect is not very strong. There is not big reduction of the boundary layer height, even with the haze conditions. Now, if you look at the left-hand side column, you have the diurnal cycle of the urban heat island intensity. quite as expected. The urban heat island is at its strongest during the winter months at night time. And you can see also quite significant reduction of the nighttime urban heat island because of the less energy at the surface during the daytime. So then, of course, also the urban heat island is much smaller. And you can also see the effect of the reduced urban heat island on the nocturnal boundary layer height also. So the aerosols not only reduce the daytime boundary layer height evolution, but also the nocturnal boundary layer height, because we have less thermal energy, we have less thermally induced turbulence, less vertical mixing, and therefore also reduced boundary layer height throughout the whole diurnal cycle. And as I said, it is a incoming solar radiation or radiation driven process, and this high seasonal variation, if we now look at the attenuated incoming solar radiation in different seasons and months, this is now the amount of reduction, so the absolute amount and the percentual amount of the reduction. For example, in different seasons, you can see here that during the summer months we have quite strong percentual and also absolute reduction compared to, for example, winter months. But we still have sufficient energy available. Even if it is reduced, we still have enough energy available at the surface so that the boundary layer can still develop high enough. And that's why during the summer months you could see that it wasn't really very strong, the effect of this reduction due to the aerosols in the air. But then, for example, in the winter months, especially the early spring and autumn, you can see a very strong reduction of the boundary layer height. Now, if we look at each month separately, so that we have the boundary layer height on the y-axis and the PM2.5 concentration on the x-axis, you can see here also that during the early spring months it is very strong, as well as also in the autumn months and winter months. But on the summer months, there's practically no big reduction at all, because there is still so much energy available, even if the incoming solar radiation is attenuated. Now, if we take this slope, the angle of the slope, so basically this regression coefficient, the beta term here at the equation, and compare it to then the available surface heat. So we have the regression coefficient, so the beta term with the black line, and the sensible and latent heat flux summed together then with the red line here. So you can see very clearly here that it follows the strength of this relationship quite well, this available energy at the surface. So during the summer months, the reduction is very small. This regression coefficient is very small because we have so much heat available at the surface still, and the boundary layer height can still develop even if it is attenuated, basically similar as it is in the winter months. But in the winter months, the energy is so low, and especially here on the autumn months or so, that even a slight reduction of the incoming solar radiation affects them so much that there's not anymore enough energy at the surface to drive the boundary layer height evolution. This is now still only 1 year dataset in this, so the future plans is to include the whole 5 years dataset that we have at the moment to get a bit more data behind it, get more convinced results. I don't expect the result to change much because it is basically the physical characteristics that it is there. We will also include the black carbon observations that we have, so that we can see better also the effect of the stabilization of the atmosphere, and also then AOD observations, where we can then, well, by the definition of AOD, to see the attenuation of the incoming solar radiation due to the aerosols in the air. And also to see the different size ranges of aerosols, to see how those affect then this correlation. So this is now still just the PM2.5 against this surface energy but we will then further continue this analysis uh, in the in the next step. So thank you. This was all I have.
Very nice talk. Thank you very much. Do we have questions from the audience?
Thank you. It's impressive work. I was wondering, because incoming solar radiation is one component of the boundary layer energy balance, right? But boundary layer growth is a multi-regression problem. It's not linear regression because surface energy balance, land atmosphere feedback comes as a complicated after the incoming radiation comes to the atmosphere surface, correct? So in the linear regression, you are actually omitting all the surface energy balance component because soil moisture, sensitive heat flux, latent heat flux is basically finally govern the boundary height. So what is my question is that between the summer and winter, did you find any kind of contribution from the soil moisture variability because that would make the big role there?
Ah, yeah, that is a good question. If I understood correctly, you said soil moisture.
Right.
Yeah, yeah. Good question, and I'm not sure. Of course, it could be possible that yeah, if it of course has an effect on it, and it is yes on the next step when we going to continue, it is definitely will include it there. So that's a very good addition to the data set that we are going to then expand for the next step. So yeah, it probably might have an effect on it, of course, because of course the winter time in Beijing is very dry. So there's no precipitation at all.
That's a big part.
Yeah, but then during the summertime there might be a lot of precipitation. So yes, of course, it is a good idea then to try to separate these also. So yes, as I said, these are still preliminary results here. So, but yes, definitely this inclusion of the soil moisture is a good idea. Then of course, what was still missing from here is for example, the anthropogenic heat flux. This can also be simulated by the SUS model, so this can also be then included in the analysis. But yes, definitely it would be a good idea to have this included.
Hi, nice presentation. So I just wanted to know, like, what was the criteria for classification of things? Like, what did you take into consideration?
In this case, we used at least at this time it was I think some standard classification by the government or municipality or it was the PM 2.5 concentration over 100 micrograms per cubic meter and the relative humidity under 75 to and the visibility under 5,000. So to exclude the fogs and only to have then the aerosol induced haze.
Thank you for your impressive work. So I just wondering if we see this image in Beijing, the haze can be very thick, so probably it block the sun. And have you checked the effect of this blocking to the growth of the boundary layer, for example? So
Yes, we can see this when we have really thick haze. Well, luckily nowadays this is quite rare in Beijing to see this kind of image. The air has been purified quite a lot since 2013. But there is kind of like a 7-day cycle on average in Beijing when the cold front comes from northwest and then purifies the air. So it changes the whole air mass and it is cleared like within a day or so. So there's usually like a 3-day cycle where the concentrations are increased and the boundary layer height is dropping. So we have then the accumulation of pollutants in a smaller area and so on. When the haze reaches certain threshold, the boundary layer height evolution is pretty much suffocated. So it just stays low and there's no diurnal cycle at all. And then you get this type of conditions. And it doesn't get purified without this strong cold front that comes from the northwest. So this is like a around 7-day cycle in Beijing typically during the winter months.
Thank you very much.
Thank you.
We will move on to the next one.